Lab 3 for Physics 2211. So for the introduction, in this laboratory we're going to calculate the net force components from observing the motion of a star orbiting a black hole, and then we're going to determine the mass of the black hole itself, and next we're going to determine the ship's velocity for it to orbit the black hole without getting sucked in by it. So as a result, we're going to get the mass of the black hole, the net force, and the parallel net force, as well as its perpendicular net force. And after that, we will get the initial velocity of the spaceship for it to escape, which I'll explain both results furthermore by its process and code. So some fundamental principles: we know that Newton's second law is which is net force equals the changing momentum over changing time, and that the net force basically equals the parallel component of the net force plus the perpendicular component of the net force. Also, we have the Newton's gravitational force law, which basically says that the gravitational force equals the gravitational constant times both masses divided by r squared times r hat, which basically only gives direction. Also, the only forces acting on the star are the gravitational force of the black hole, and the only forces acting on the spaceship are the gravitational force from the black hole and from this planet. So the net force acting on this problem is only gravitational force. We also know that the universal gravitational is non-constant, so the average velocity equals the final velocity. And if the parallel net force is in the same direction as its motion, the object is speeding up. If not, it's slowing down. Also, that the perpendicular net force only changes the direction of the motion of the object. First part of the experiment, here we have the glow script, which was used to determine the mass of the black hole. As you can see, here's my personal email address, and as we scroll down, we start here with the gravitational constant, with the mass of the star, and the time intervals between the important data points, which is 1 day in seconds. Later, we can here we're actually calculating the initial velocity and the final velocity, and also integrating to get the final and initial momentum by multiplying the star mass with its velocity. And then we calculate the change in velocity and the change in momentum, subtracting the final minus the initial of each. And as we can see, the PDT, which is the change in momentum over time, equals net force, as we can see from Newton's second law. As we go down, we can also calculate the parallel component of the net force, as well as its perpendicular. And here, these are basically just the arrows representing the net force and the parallel and perpendicular components. We can see the star orbiting around the black hole, and as you can see, these numbers over here are the mass of the black hole, which are like it's like an estimate over time. Once it ends, we'll get the final value, which is 1.529 times to the 10 to the 34th, and we also get the values for net force, for the parallel net force, and for the perpendicular net force. Use a glow script to determine the velocity needed for the spaceship to escape the black hole. So as we can see, we have here our initial conditions, which are basically constants. We have here as well gravitational constant, the mass of the planet, the spaceship, and time. And as we can see here, we have the initial conditions for the spaceship to escape the black hole. So the speed for the spaceship was determined using a trial and error. Then here we have a calculation loop, which we use to determine different net forces. So here first, for example, we determined the gravitational force on the planet by the black hole and the gravitational force on the planet by the spaceship, which by adding them up, we got the net force on the planet. As well as here, we got the gravitational force on the spaceship by the black hole and the gravitational force on the spaceship by the planet. And as well, by adding this up, we got the net force that was on the spaceship. Okay, so over here we can see to make things move in the program, we basically applied Newton's second law and the position update formula to make the planet and the spaceship move and interact in the program as well. So here when basically we run this program, we'll get something like this, which basically tells us that the rocket successfully escaped the black hole. So what does it mean? So how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So basically, we know that they are the same, as the Newton's second law states that change of momentum over change in time equals the net force. But we know that mathematically they are the same, but getting the changing momentum is easier than the net force itself. So now, what if the initial velocity what initial velocity will your spaceship need to have in order to to enter into some kind of orbit around the black hole. So to do this, what I thought is that to orbit, the spaceship should have a similar velocity to the planet, but the y component should be larger and the x component should be smaller and negative as well to avoid collision with the black hole, similar to the code we ran earlier. But honestly, I wasn't able to do this, but this was my best try. I don't think there were many sources of error in this experiment, and thank you very much for your attention.